Welcome to our chapter on the universe. This is going to be a very brief overview of something that we spend an entire semester on in Astronomy 102. So if you're interested in this particular topic, please think about signing up for that course. We do teach it here at Ivy Tech virtually. Most of the time it is taught by me. But all of the things that are in here, we're going to go through it really, really quickly because for our purposes in physical science, there are only a few key things that I want to emphasize. But as you can see from the thickness of the PowerPoint printout, if you were in my face-to-face class, you got one of those, or you can see from the number of slides that there's a lot to cover. So I'm going to jump very quickly through a lot of the materials because I know it can go on for a very long time. So I apologize for that. If you want more information, feel free to send me a message and I can give you all sorts of follow-up pieces, including things that we use in the 102 class and things that I've studied over the course of time in other places. But let me share my screen here and let's get to the PowerPoint. And here we are. So let's go to our slideshow. And we're going to look at the universe in general. We've already talked about the solar system and moons and asteroids and comets and planets. We didn't talk about the sun too much, so we'll talk about that a little bit more here because the sun is a star and stars make up galaxies. Galaxies and stars are the key components in the universe, as this slide will talk about. We have been studying the universe in great detail since the last century. Really, the 1920s are when we began to look outside of our own galaxy and know that we were looking outside of our own galaxy. And in the 1930s, we began to look in other spectra like radio and then later infrared and ultraviolet and X-rays and things like that. So we've been able to gauge the universe as a much larger study for a very long time. Unfortunately, most of the different types of wavelengths of light don't make it through to the surface. So we've had to wait until we could get things above the atmosphere, infrared, ultraviolet, X-rays in particular. Certain parts of infrared do make it somewhat through the atmosphere, but also visual light tends to get messed up by the atmosphere. So we tend to put things on mountains where they have less atmosphere to contend with as things are going. Keep in mind the difference between astronomy and astrology. I know we've talked about this in our face-to-face class. Astrology is really a psychological and religious framework of trying to figure out if the stars have any particular effect on what we're doing in our life. Astronomy is what we're doing when we're looking at the sky and we're trying to figure out what's there and how it moves and why it does what it does. Very different kinds of things. When you think astrology, think psychology and religion. When you think astronomy, think physics and math and chemistry mostly. When we're thinking about where we are in the universe, it works for us to think about ourselves sort of in the middle of everything, because in fact, from our perspective, we are where we know we're not in the center of the galaxy or in the center of the universe, but from the center of where we're looking at things, obviously we are here. This picture shows the cycle of stars around the pole, and this is a time-lapse image. So if we were to sort of look at it, we could see that this arc is probably taking about 2 hours. This arc is probably taking about 2 hours. Say if this were 11 o'clock and this were 1 o'clock on a clock, that's 2 hours. If it were 24 hours, it would be going all the way around. Our sky seems to rotate around us, and it rotates on the poles, the North Pole and the South Pole. Halfway between those is the equator, but we're tilted. We're tilted 23.5 degrees. So we also have this other line in the sky called the ecliptic. And that seems to be, from our perspective, where the sun, the moon, and the planets all hang out. They don't hang out near the North Pole. They don't hang out near the South Pole. They're always in between, but not strictly precisely in between. They are a little bit off, and that's because we're tilted. Twice a year at the equinox, they are overlapping with the equator exactly halfway. But the rest of the time, sometimes they're higher, sometimes they're lower. As I'm making this video, we're just after the summer solstice. So the sun would be up here relative to the North Pole, and our Earth is tilted a little bit towards the sun to the north. That means in the south, it's tilted away. So this talks about the equinoxes, halfway point. Equinox means equal night. And then, of course, when we're talking about the solstice, that's the longest day and the shortest day of the year. Those will be opposite in opposite in opposite hemispheres. So when the summer solstice is in Indiana, it's the winter solstice, shortest day of the year in Australia. When it's the summer solstice in Australia, which is going to be in December, it'll be the winter solstice for us. So if you draw a line between the poles, we get the prime meridian, and that helps us to map out where things are in the sky. And we can use longitude and latitude in the same way that we use here on the planet. But we also have other measurements, which include right ascension and declination, which is sort of how far east and west and how far north and south things are. That way we can tell people in other locations where to look for things in the sky, and it won't be based on where we happen to be standing at the time. I'm not going to go into the celestial distances here too much for purposes of our class, but just be aware that we can do that. We've already talked about parallax in our class, so I don't need to go too much into this. Just remember, this is the idea that where you close one eye and put your thumb up, and then it covers something, and then when you open the other eye and close the eye that's seeing things, you can see things shift around. That shifting helps us determine how far away things are, and we can do calculations that tell us about that as well. Stars are effectively too far away to be seen with the naked eye. In parallax, you can do that trick with the moon, you can do that trick somewhat with planets, but it really took good telescopes for us to be able to start observing parallax. And the first person to do that was in the mid 1800s, as you see here, Frederick Bessel. Our sun is also a star, though. So when we talk about how far away stars are, we're accepting the sun. We think about the sun as something a little bit different from the other stars. In fact, it's the same as other stars. It's just enormously close up. Our sun is about 100 times the diameter of the Earth, so you could put 100 Earths across the face of the sun. It is vastly more powerful, it's vastly more gravity, it's vastly more mass than the Earth. And it's roughly 93 million miles away, although sometimes we're closer to it and sometimes we're further away. The sun's structure has a photosphere. That's what you see when you're looking directly at the sun. Don't look directly at the sun. But it's about 6,000 degrees Celsius, about 6,000 Kelvin, more or less, a couple hundred degrees here and there. 75% hydrogen, 25% helium, with a trace amount of other types of elements that are in there. Sunspots are patches that are cooler. We have those operating on an 11-year cycle called the sunspot cycle. We had a period in the 1600s after we discovered them that they stopped showing up for about 50 years, and we call that the Maunder minimum. That also seemed to coincide, we don't know whether it's cause and effect or just happened at the same time, as the little ice age in Northern Europe, where things were dramatically cooler for quite some time. This picture shows a granularity. Each of these little dots is a granule. Each of these little dots is probably close to the size of the Earth, maybe a little bit smaller, but not much smaller. This is the sunspot, which is about 1,000 degrees cooler than the rest around here. Although if I held this up in my hand, it would incinerate my hand instantly. It would also be the brightest thing you've ever seen in your life, in real life. But it looks darker because the rest of the area here is much, much hotter. This dark patch is called the umbra. This area around is called the penumbra, and it is magnetized. That's why it looks different than it is. And the sun has to be very powerful to turn something like hydrogen, which is non-metallic, into something that is pretty magnetized. The sunspot cycle goes on an 11-year cycle, but each 11 years, the poles flip on the sun, not the physical poles, but the magnetic poles, which means to get from north to south to north again, it's actually a 22-year cycle that's there. But if you say 11-year cycle, you're just fine. When the sun has explosive incidents, we get those called flares and prominences. We can see one here in this wonderful image. It will throw extra particles into the solar system called the solar wind. And when that hits our planet, we get the northern lights. Here in Indiana, over the last couple of years, we've been seeing more northern lights than is usual because we've had quite a bit of extra particles that are being thrown into the solar system and therefore being caught by the Earth's magnetic field. Here we cannot see at the top here another little prominence that seems to be fading. Most of the material that gets thrown off the sun will in fact get pulled back into the sun by its gravity. On above the photosphere, we have a wispy area of atmosphere called the corona. This also is helping to generate the solar wind, which goes all the way through the solar system. Deep inside the sun, we have a nuclear reaction going on. At the core, we've got about 15 million degrees 15 Celsius, 15 million Kelvin. And in here, we have a fusion process, which is turning hydrogen into helium through something called the proton-proton chain. What happens is two protons get slammed together at high temperature and speed. They glom together with a third proton particle to form the basis of a helium particle. These triads then slam together to form a stable helium particle and re-release some of the original hydrogen particles back into the mix. And that just keeps happening over and over. As this happens, the process generates energy. And this energy is accumulated according to this famous equation of Einstein, E equals mc squared. E is energy, m is mass, and c is the speed of light. And in the terms of units here, it is the speed of light squared by meters. So it's 300 million meters instead of just 300,000 kilometers. So 300 million times 300 million means you only need a little amount of mass to turn into a huge amount of energy. So more energy is generated by the sun each second than the whole human race has used in its history. So that's a lot. And the sun will probably continue to burn hydrogen into helium by the fusion reaction for another 5 to 7 billion years. Right now, we only get a small portion of that energy because most of it's going everywhere else in the solar system. So we do get some. We could capture more if we built equipment, solar panels, other kinds of things outside of our atmosphere to collect things. And that actually has been the basis of solar system kinds of science fiction, as well as forward planning for the future. Our sun is a star. Most stars are about the same size as the sun, or slightly bigger, slightly smaller. Really big stars tend to be rare, but they all have one primary thing in common. Through most of their life, they are changing hydrogen into helium. They are going into a fusion reaction. Some stars have solar systems like ours. Some have two stars that are going around each other. Some are part of multiple star systems. Alpha Centauri, which is the nearest star to our system apart from the sun, is actually two stars going around each other with a third star going around the two. So when we look up at the sky, we also find it convenient to think about them in terms of patterns, constellations, the Big Dipper, Ursa Major, the Little Dipper, Ursa Minor, Orion, Libra, Aquarius, all of these different ones. There are 88 constellations in the official modern sense of constellations, but different cultures have seen different things in the sky over time. So constellations will come and go depending upon which part of the year we're in. Orion, for example, is prominent in the fall and the winter. Some, however, if they're close to the poles, like the Big Dipper and Little Dipper, will be there all year round for us. Asterisms are parts of constellations. So the Big Dipper technically isn't a constellation. It's part of a larger constellation called the Ursa Major, the Big Bear. But a small part of the Big Bear is the Big Dipper. A small part of the Little Bear, Ursa Minor, is the Little Dipper. So these, but they're well-known patterns for us to see. So here's the Big Dipper and the Little Dipper inside the larger constellations. Now, this star here, the tail of Ursa Minor, is actually Polaris. That's the North Star. And if you look at the Big Dipper, you can see the two bowl stars here. If you drew a line between them, they go all the way up there. We call those pointer stars. When we're looking at stars, we can think about them in terms of brightness and dimness. Some of them are brighter than others, but the way we see them depends upon not just how bright they are, but how close they are. So how bright they are to us is called apparent magnitude. And this was a scale that started in ancient Greece and continues to this day. So some of the stars are higher in magnitude, some are lower. Think about them like golf scores. The bigger the number, the worse the score, the lower the dimness that is. The sun, for example, is minus 27, so that's really, really low. The brightest star in the sky, Sirius, is -1. Sirius is the fourth brightest thing. That might be a quiz question. Sirius is the fourth brightest thing in the sky. Venus is the third brightest thing in the sky. The brightest is the sun. The second brightest is the full moon. Obviously, the moon changes over time in its brightness. Venus does as well, because sometimes it's dimmer than others. But in general, Venus will be the third brightest thing in the sky. Sirius is often the fourth. Sometimes Jupiter will compete with that. So obviously, some stars are going to be brighter than others, like just like some light bulbs. Some are 100-watt bulbs, some are 500-watt bulbs, etc. So we call that the absolute magnitude, and we can chart those on what we call the HR diagram. The HR diagram, if you come to the 102 class, is a major part of our study. Any star that is here in the middle is going to be called a main sequence star, and these are the stars that are burning hydrogen into helium. They run out of hydrogen, they go up into this area here, the transition area. Notice that Betelgeuse and Polaris and Aldebaran and Pollux and others that are well-known stars are up here. They're beginning to run out of fuel. Once they've sort of exploded or let go of most of their material and they're a leftover zombie star, then they're down here in the white dwarf area. So when we're looking at these, we have at the bottom here, temperature gauge. Notice that the higher the temperature, the more blue it is. The lower temperature, the more red it is. That doesn't necessarily indicate size, because you can have a giant blue star like Rigel and a giant red star like Betelgeuse. Both of those are in the Orion constellation, by the way. Also over here, notice from the bottom up, we're going from dimmer to brighter. And you can be ultra hot and be rather dim if you're small, but you can be really hot and really bright. You can also be small and dim. So dim to bright is on this side. This is also the absolute magnitude. And we have our spectral classes. That there's a long history about that, and I'm not going to go into it. But if you are interested, look up a person named Annie Jump Cannon and the Harvard calculators. That is a really wonderful story about that. Maybe I'll do a video on them someday. When we're looking out beyond this, we see that there's a lot of gas and dust in the universe. Some of it actually extinguishes the light that reaches us, so it's sometimes hard to see beyond our galaxy or different parts of our galaxy. It's hard to see into the center of our galaxy, for example, with regular light, because the gas and dust obscures things. Sometimes this gas and dust collates together into what we call nebula. A nebula means cloud in Latin. There are bright and dark nebulas. There are some that will emit light, or there are some that will reflect a lot of starlight off of them. This is the Orion Nebula. It's a great emission nebula in the middle, and parts of it are, in fact, also reflective nebula. This one over here, this is actually a secondary nebula called Demarian's Nebula. And then these dark patches in here are actually parts of the absorption nebula that is not emitting light as much as it's absorbing it there. Some of the best known dark nebula, not dark matter, by the way, that's a very different thing. This is just darker in terms of coloration and brightness. This is the Horsehead Nebula. This is also in the Orion constellation. And from our perspective, it looks like a chess piece, like a horse. When we're looking at energy coming off of low mass stars, it's usually going to be in the cooler range. While the gas and dust collates together, it heats up and usually it will glow in a smaller thing. It will turn into an actual star when we have a fusion reaction happening in the center. So the gas and dust will collate together. It'll turn into a star. It'll burn hydrogen and helium. So it'll start off the main sequence, then leave the main sequence when it runs out of hydrogen. It'll become a variable star trying to adjust internally, and then it will puff most of its material away into what we call a planetary nebula. So if it's a high mass star, one of the things that happens is that it will have a big explosion. In both of these cases, there's a point of time where it's a variable star. The best known of these is Polaris, our North Star. A small star like our sun will turn into what we call a planetary nebula. Has nothing to do with planets, unfortunately. Of course, astronomy often does this. The earliest photographers who took pictures of these thought they looked like planets. Now we see things like this one, sometimes nicknamed the skull. We have material coming off the star, and the core, the leftover core, engine core at the center, is the white dwarf that's there. The white dwarf will be superheated and super compact, lots of material forced into a tiny spot. Here, this is Sirius. Sirius is actually a binary star. Again, fourth brightest thing in our sky. It is and brightest star apart from the sun. It's actually Sirius A here and Sirius B. This little dot down here is a white dwarf, which is the companion star that's already burnt itself out. Well, and I don't know why it says there it's at 5 o'clock, because this would be actually 7 o'clock. I think the picture is inverted. That's there. So if a star doesn't have enough material to come together and kick on its engine in the center, it becomes a brown dwarf, and we've found hundreds and hundreds of these. The planet Jupiter is almost a brown dwarf. So as a star begins to fade out, it will sometimes, if it's like a companion star with Sirius, begin to leach material off of its companion, and that can cause an explosion. And that explosion we call a nova, or a new star. But if it's a huge star that itself just explodes at the end of its life, we call that a supernova. And there are two different types of supernova, one from the star itself and one from a star that's accumulated extra material and become oversized. And we can tell the difference from the spectral lines that come off of them. The Crab Nebula is a great example of a nebula left over from a supernova explosion, a big star exploding. And it filled the sky in the year 1054. You could read by it at night, you could see it during the daytime. We have a supernova explosion in our galaxy about once every 100 years. We have not had one in 400 years. We had one in the late 1500s and one in the early 1600s. We call them the Tycho supernova and the Kepler supernova. But we're overdue. That's why I say Betelgeuse, Betelgeuse, Betelgeuse. When it explodes, we'll be able to read by it at night. We'll be able to see it during the daytime. It will be fantastic. It's not going to disrupt anything on Earth, but it will be a huge, huge thing. And it's due to explode any day now. But in astronomy, any day now means sometime within the next 10 to 100,000 years. The Crab Nebula was recorded in a lot of different cultures when it happened. And one of the things that we have discovered at the center of it is that there are lots of extra materials that we wouldn't expect from a star. So supernova explosions actually create new materials. Anything above iron, like gold and zinc and uranium and other things in terms of our elements, are created during supernova explosions. What's left over at the end can be a neutron star, which is even smaller and denser packed than a white dwarf, or a black hole. A pulsar is a very rapidly rotating neutron star that's throwing out a magnetic and radio pulse, and it acts sort of like a lighthouse. These things can go around like 30 times a second. They're about the size maybe of Bloomington, maybe the size of Fort Wayne, but they weigh as much as the entire North American continent, if not more, in per sort of bucketful. So they actually can have more mass than sort of a quarter of the sun in some ways. So this is in some of them. So as they spin rapidly, they're also generating huge magnetic areas. And sometimes they're also called magnetars. You may hear a magnetar. The VLA, the Very Large Array, is set up to detect these kinds of radio waves. And in addition to others, you may notice this facility in some movies like Contact with Jodie Foster. The Crab Nebula has at the very center of it a pulsar that spins around 30 times a second and emits a pulse. When we first saw it, we thought we had discovered cosmic GPS, and we thought this was a signal from an extraterrestrial intelligence. Black holes tend to be a very popular subject. This is what happens when there's just not enough structural and energetic power to keep gravity from pulling the material all the way in. What keeps the sun from collapsing in is the energy that it's producing. What keeps a white dwarf and a neutron star from collapsing is just the sort of structural force of the material that's in it. But the reason why a neutron star, which weighs more, is smaller than a white dwarf is because the stuff is getting scrunched more and more and more. And there is finally a point where it just can't hold up. And that's usually 3 to 5 times the mass of the sun. It scrunches down all the way to a point. And no, not even an inch long, not even half an inch wide. It just goes completely down to a point. All the material scrunches down into that. But around that area, light and everything else is being bent so much that nothing can escape it. So at the edge of where inside everything's being bent and outside everything is being sort of curved around, but not quite pulled in, we call that the event horizon. Because the event horizon, we can't see anything inside. We can't see any events inside. So it's like looking over the horizon, you can't see it. That's why it's called event horizon. But usually around a black hole, there's going to be a disk of material that's spinning into it. And that stuff is creating X-rays and gamma rays, usually more X-rays than anything else. And when we see a black hole that is nearby another major star and is sort of devouring the material off of it, it generates lots and lots of X-rays. The first one is in the constellation Cygnus. That's the first one we discovered. And Cygnus X1 is the companion to a large blue star. The large blue star has material being leached off of it, and it's literally spinning into the black hole. High mass stars and low mass stars form the same way. High mass stars are hotter and brighter than low mass stars. High mass stars burn out faster than them. And what they will eventually do, the high mass stars, is they will have supernova explosions and turn into neutron stars or black holes. So mass is the key determiner. If you are a high mass star, you end up as a neutron star or black hole after an explosion. If you are a low mass star, you turn into a white dwarf with a planetary nebula around it. So this is what happens. And of course, if you're a planet or a moon or something like that, you just keep going until something hits you. Basically, the only thing that's going to destroy a planet or a moon is going to be some kind of collision. So when we collect the stars together, we collect them into galaxies. Galaxies can be any number of shapes, including spirals, irregulars, ellipticals. I think you can look for galaxies in one of the Zooniverse projects. Hubble is one of the first persons to figure out that galaxies are outside of our own galaxy, that there's more than just the Milky Way. He was actually a Rhodes Scholar, which means he went to Oxford University, like a lot of people, including Bill Clinton, who was president, and Richard Lugar, who was our Republican senator here in Indiana. Hubble also taught basketball, was a basketball coach at New Albany before he became a Rhodes Scholar. So he has an Indiana connection with us. Elliptical galaxies are sort of blobby galaxies. I love this one because sometimes it's called the face. It looks like the universe is just sort of having a meh day. These are blobby galaxies. You can see sometimes they're a little bit more elongated, sometimes they're more spherical. We can also see sideways galaxies, which are sort of spiral galaxies. These over here are sometimes called the eyes. Those are also elliptical galaxies. Spiral galaxies, this is the nearby Andromeda galaxy, closest spiral to us. It also has some elliptical galaxies above and below it as part of its entourage. Here's the Whirlpool galaxy. This has a companion galaxy over here, although some people think of this as an extension of the regular galaxy that's here, but it looks like it's a second galaxy that's interacting with it. But we can see the spiral arms pretty well. This is also a spiral that we're looking edge on. It's called the Sombrero galaxy. Then we have barred spiral galaxies where we have the arms coming off the center, sort of in an elongated shape. Our Milky Way is like this, but we have no pictures of the Milky Way from the outside. Then irregular galaxies, these are blobby shapes that usually have happened because they've been had collisions with other galaxies, or they are being torn apart by the gravity of other galaxies. These, the Large and Small Magellanic Clouds, are near our galaxy, and our galaxy is eating them for lunch. So they are being misshapen by the galactic gravity of ours that's there. Galaxy differences are quite a ways away. The nearest galaxy to us is probably about 50,000 light years away from our galaxy, but again, it's being pulled in. The Andromeda galaxy is 2.2 million light years away from our galaxy, and our galaxies are actually coming towards each other gravitationally. But the Milky Way, if we were to look at it from the top, this is what we think we would see. There are 2 to 4 arms. It's hard to determine exactly how many arms we have because we're in the middle. And this is what it looks like on the side. We have clumps of stars that go around outside of our disk of material. This is what it would look like sort of on the edge. This is actually looking at it from the inside, but looking at cosmic background radiation. Globular clusters are clumps of stars that go every which way around our disk of material. Some galaxies are overpowered. We call those quasars. And those are quasi-stellar objects because they sort of looked like stars when we first discovered them. But they are powerhouses of radio energy. In the middle of them, they have supermassive black holes. Here's one that probably has a black hole somewhere around 1 billion solar masses. We have one in our own galaxy that's only 2 to 4 million solar masses there. When we look out into space, we're also looking back into time. When we look at our local group, for example, when we look at the Andromeda galaxy, we're seeing light from 2 million years ago. When we look at our nearby cluster, we're looking at light from 15 up to 15 million light, years ago. So most of the galaxies in our local area are small. They're sort of dwarf galaxies. Here's the Milky Way and here's the Andromeda. Triangulum is a sort of third, that's M33, a kind of a third galaxy that is spiral and good size. But all the rest of these are sort of clumpy galaxies that are rather small. And they're all being essentially pulled together by mutual gravity. Now, somewhere out there, there's something called dark matter, and dark matter doesn't glow with like infrared or ultraviolet or X-rays or anything like that. So we don't know exactly what it's made of, but we can tell from the gravity, the way it's pulling things around, that in fact there is the stuff that's out there. So we're sort of guessing that there might be some wimpy particles, the massive particles that don't interact all that well with stuff, or massively compact objects that are floating around outside of our galaxy as well. When we're talking about these kinds of things, we're looking at something called cosmology. We're looking at the greater structure of the universe. When we're looking at these things, we have to take into account Hubble ideas of everything going further away from us, and the further away it is, the faster it's going, which tells us that the universe is expanding. This has been known since the 1920s and 30s, so this is not a new idea. But this is because what happens when things are going away from us, they are red shifted. When things are coming towards us, they are blue shifted. That happens on Earth, that happens in the solar system, that happens in the galaxy. That's what's happening out in the universe. And the further away things are, the greater the redshift tends to be. So it's a very simple relationship that Hubble figured out. So it's basically called Hubble's law. The greater the speed that it's going away from us, the further away it's going to be. That basically means we're not the center of the universe, but everything is getting further away from everything else in the larger sense. In the local sense, we're still being bound together by gravity. So eventually, everything will be receding away from each other much faster than it is. And that we often use this raisin bread analogy. If you're on this first raisin down here, and you're in a loaf of bread in an oven where everything is going away from you, each of these raisins is going away from you more or less at the same speed. But from your perspective, the one that is further away at the start will seem to be going further away faster. Now, if you're on that raisin over here on the left, then the original raisin will seem to be the one that's going away further and faster. So there is no technical center of the universe in this sense. From this understanding, right now we calculate the age of the universe to be about 13.7 to 13.8 billion years. That is a number subject to change. When I took this class 25, 35 years ago, maybe closer to 40 years ago, that number was closer to 20 billion years because the best data that we had at that time was giving us that result. We've since had a lot more discoveries, a lot more probes up above the atmosphere to take a lot more readings. So this is a better number, but it is subject to change. When we are dealing with certain objects in there, however, it gives us some anomalies. So we do see some different kinds of plays together, and that's still under investigation. That's still under sort of under construction, as it were. How is the universe expanding away if gravity always pulls together? Well, that's where dark energy comes into play. And of course, if everything is expanding away, that means if you play the tape backwards at some point, we had to have been all in a big crunch. And that's where the Big Bang comes from, the idea that we began with a rapidly expanding center of things. And we're able to sort of see some leftovers from that. Hydrogen to helium and background radiation and background red shifting of different things all play together into putting this as the primary idea for the way the universe was begun. In 1980, we had this idea that instead of just constantly going up, though, we have acceleration points. So we call that the inflationary model, where we sort of have these different kinds of areas, which include the fact that we might have more than one universe. That's where the multiverse comes from. That while we're forming over here, there's another one forming over here, and we're separate enough now that we're not able to see or communicate with what's going on there. So you can take a look at this graphic here, and you can sort of see we had a big hyperinflation. We then had a sort of a steady period, but now we're accelerating again with dark energy. So those are the things that are under investigation right now in astronomy and astrophysics. So let's see. I hope you found some of this interesting. There's a lot more I could say about pretty much every topic that we covered in that. And I think you could probably tell by my going so fast and trying to get everything in that there's just a lot of stuff there. So I thank you for paying attention. If you've made it this far, please comment in the area down below. Also, if you're so inclined, please subscribe to my channel. I think I'm only about 40 people away from being monetized. And as I keep saying, if the channel's monetized, we will let the money go to scholarship funds at Ivy Tech for fellow students. The whole tens of dollars that we would be making off of this channel. But as my poster says, keep calm and carry on. I hope you have a wonderful day. Thanks.